welcome back to the uh, data science course conducted by IIT Guwahati. We were discussing the various mathematical parts that are required for the data science, and we right now we are discussing about the statistics. Right, in the previous classes, we were looking at the various distributions, the maths behind that, the various problems related to that, simple problems only, not the difficult ones, and also writing the code to get the probability out of for a given distribution using the programming. All right, so these were the topics we were discussing earlier. Okay, and we'll be continuing from where we left. So recall, in one of the classes we had started a part of the statistics, and then we deviated to the distributions because we needed the distributions and the concepts related to the distributions, and now we are coming back. Okay, so recall the slides that were being shown in one of the classes, and we were halfway through, right? So today we are continuing from there, but before that I want you to recall what was being discussed in those slides. All right, so remember the word sampling, right? We have a huge data set or huge okay, let's go to the example itself, right? I want to go for an opinion poll, and I want to give my view about who is going to win the particular election, right? So you cannot go and ask each and everyone in the constituency. So what you do, you randomly ask randomly ask people about this. So you select certain number of certain number of people, right? That's what is called as a sampling. You sample it out and you ask. Again, sampling, there are several ways of doing sampling, but just recall this picture. There is the huge amount of data which is available for you to do the sample is called as a population, but you are not going to ask each and everyone, right? You will be asking few at random according to the capability, time, money, whatever you have, right? So that was the concept of sampling. But our idea is that in order to get the most accurate result out of it, right? In order to get a most effective result that you can give, so your prediction should be as closer to as possible to the actual result. So you need to design something, right? So that part we were discussing there, which is called as a sampling design. Yeah. No, we just start. This is the first slide. Okay, don't worry. This is already covered, right? Actual topic will start at a later stage. All right. So, no, this is actually from old class. I am trying to recall. Okay, so don't worry. Nothing actually being taught right now. All right. So let's go with the flow. All right. If you have doubt, I'll clear that. Statistics. All right. Okay, we are still in the statistics. Right. Fine. So first topic we had discussed already was a sampling. Okay, so you have a huge population. You cannot go and ask each and everyone in the population about your opinion. So what you do, you pick some people out of the population at random, and then you will try to make the guess who is going to win, right? So I need to design something, how many people I should ask, right? So etc. Many points are going to come, right? That we'll see. So after that, we discuss what is called as various strategies possible, right, in the sampling. So in case of a sampling, right, first thing is very simple. Randomly you choose. You don't follow any rule. Whoever you meet in a constituency, you keep asking the question, right? Whom you voted, and what's your opinion? Who will win? You can ask that question as well, right? So that was the first case, and randomly you pick people, right? There is no restriction saying that you have to go for the same number of people always, right? So that's the overall idea. Okay, So coming to the drawback, it is not practical, right? So in the sense, there is a restriction over here saying that you should ask people who are independent and unbiased. There should not be a bias, right? So this maintaining of this particular condition becomes very difficult when you go to, right, the random selection of the samples. Okay, just try to recall, right? This all these slides we already have covered. So then we have what is called as a stratified sampling, right? So divide the whole population into small number of groups, right? The example I gave is go to the booth level, right? So because the whole population is divided into booths, right? So the whole constituency is divided into groups, and group level, if you go to a booth level, you may get more details because their booth is arranged in such a way that the locality is the same, their mentality will also be same towards a problem, not in general. Okay, they may face the same problem, so they may have a, you may get a better idea, better view. So for a given small group or homogeneous group, what you do, you ask, then you go for a randomness. You apply randomness over there. All right. So that is the idea over here. Right. So again, you can see that even in case of machine learning, we have a concept called as a stratified train and test data. Right. So I have a machine. I want a machine to learn something. So what we do, I have data set, right? In the data set, I'll divide them. I'll make some groups, smaller groups, and group wise, I'll try to train my machine. Okay. Similarly, for testing purpose, you keep certain amount of data set separate as a testing data, which you don't give it to the machine during the training. So that is very much necessary in order to understand the understand how much machine has learned. Okay, so this is the overall idea. So in case, even when you go for what you call as a practical application of building the machine learning models, we will be using the same similar idea over there. May not be exact, it may not be the exact one, but there is what is called as a stratified train and testing data. Okay, so since there was a question about training and testing of the data, I'll try to give some hint about what you are going to do in the training, what you're going to do in the testing, etc. now itself, so that some idea you get. Okay, so this will be dealt in very depth, okay, at a later stage, but right, since there was a question, I'll try to give a hint about that. So let us say my objective is to build a classifier. Okay, classifier is the one which classifies the given input into the classes. Like for example, let's go for a very simple case. I have 10,000 images of dogs, 10,000 images of cats. So you see, classification, if I build a model, machine learning model should be able to classify the given image into one of the classes. What are the classes possible here? It's a very simple case, like dog or cat. I give a testing data, assume that training is over. I give one of the data as a testing, like an exam, right? I give a question. You will answer that, okay, to this question, this is the answer. In a same fashion, right? Machine should answer that. When I give a testing image, it should be able to classify that, okay, this belongs to dog class or a cat class. Okay, so what is the output? Will it tell dog? Will it tell cat? Will it do something? We'll see that later. Okay, so the objective is that it has to tell me which class the input data, testing data belongs to. Overall idea is that, yes, sorry, edge impulse. What is that? I didn't get. Can you type the in the chat box, please? Okay. Okay, we'll see that. So the idea is that, right? You understood the overall question that the machine is right facing. So in order to do that, anyway, we have various machine learning algorithms which will help the machine to understand. How does it understand? You build a model. How do you do the model? There is mathematics behind that. So you need to write an algorithm according. All right. So that part will be covered at a later stage. We need fundamentals of maths to be done. So we are starting with the statistics also. Okay, fine. Then whenever I give, so in order to make this happen, what you are supposed to do, you are supposed to train the machine. Okay, so training in a sense, you say I'm taking a class. That's actually a teaching. So teaching and training go hand in hand, let's assume. So consider the machine to be a student. Okay, the machine which we are trying to build. So I'll say that, okay, I have 10,000 images of both classes, cat and dog. So what we do here is we don't teach everything, right? So like when I take a class, maybe I teach only 70%, remaining 30% is left to you to learn by yourself. Okay, say something like that. What we do, we divide whatever I'm supposed to teach. That is, my syllabus is 10,000 images in both classes. So 10 plus 10, 20,000. So what we do here is that during this, the whole process of training and testing, we split our data set into two parts. Okay, higher portion for training and a smaller portion for the testing. Something like the standard is the standard used is 70-30 or 80-20, something like that. You can do anything. There is no fixed rule saying that you have to do the same. So assume that I divided this into 80 into 20%. 80% for training, 20% for testing. Okay, so how much it becomes out of 10,000? 8,000 for training the machine, 2,000 for testing. So totally 10,000. This is repeated even for the other class, two classes. So totally you can make a calculation how much, right? So I have a training data, I have a testing. Right. So what we do during the training is that we give the data in the sense the image one by one to the machine. We pass it, saying that, okay, look at this image. This is a dog. Next, I'll take another image. Randomly, this will be shuffled. Okay, because I cannot keep teaching the same thing again and again. Machine's learning capability is reduced in that case. If I keep giving, okay, this is a dog. Next one is also dog. Next one is also dog. Next one is also dog. No, that's not suggested. So bring variety into picture, right? Variety in the sense, take one from the dog, next from cat, again from cat, then dog, then dog, then dog, then maybe randomly cat. So like this you have to. So again, everything is programming, right? Nothing to worry. You write a proper code, everything will be done for. So machine gets it trained. Okay, so completely finished, right? How much server data you have kept for training, you complete it. So once that is completed, now the testing part comes into picture. After you have learned, we give a test to you. Understand that how much you have learned. And during the test, I will not ask the questions which I taught you, right? So that's the point. You see, I kept 2,000 image in both categories separate. That was not being used for training. Machine does not know. Machine has no idea that what I have in the test data. Some of the data may be the same data which is used for training, obviously. So your questions may be, some part may come from what I already taught. Something will be definitely different, right? It's a new. Like I use a bigger dog while training, right? Maybe, right? I give a small dog for testing. You should be able to classify, that's all. So this is the idea, right? Behind the separation of the training data and the test data. Okay, so when the test data is given, say 2,000 from dog class, 2,000 from cat class, right? So out of those 4,000 images, how many images are properly classified? Dog into properly dog. I give a cat image is properly classified into cat, right? That total sum divided by 4,000 into 100 will be your accuracy. Okay, something like out of 100, how much you score, right? So that is one of the parameter to measure the performance of your model. Higher the accuracy, you can say that yes, machine learned, right, in a very sophisticated fashion. Machine is able to classify anything which is unknown to that machine, right, but belongs to the same class. Okay, so This is the overall idea about the training and testing. Inside this, we have stratified, which is mentioned over here. Let's remember this word. We will be using it at a later stage. Okay. Then we looked at the other strategies that are going to be used in the whole process. Okay. So that is, one is the systematic, right? So the example is choose kth sample in a sequence, always choosing the same thing. Okay, like I go for a dictionary, right, or directory. Maybe directory is a better example. So I have to select people whom I can ask the questions about the poll, but I will follow a route. I take a dictionary. Dictionary corresponds to the telephone numbers, address of a particular, say, constituency. I'll say that every page 10th number, whoever is there at 10th position, I'm going to ask them. So that's what is the systematic. Opportunity is first n sample. I don't worry, right, how many people are there. I'll choose first 4 people from every page. That's what is the second category, opportunity. Then the reservoir sample, right? Reservoir sampling is select k number of samples from n, but n is unknown to you. For example, right, a survey. Yeah, okay, we have a question here. Edge impulse or image or object classification as an example of ML. Yes, yes, yes. So ML, actually inside ML we have varieties of what you call types of classification, right? In case if you go to image, right, even inside the image you have varieties of possibilities. One of such possibility is a object detection, detection of object, right? So irrespective of the position of your object in the image, you should be able to identify that. So you trained cat at this position, but in the test image I give a cat here. So are you able to identify that or not? So that's also a classification issue. Object detection is the proper heading for it. All right. So okay, moving ahead. So then we had discussed what is called as the reservoir sampling, when you don't know the total size, but still you have to take any k number of out of. Okay, so best example is maybe you are going to do a research based on the number of people visiting your website. Okay, so I have no idea how many people will visit my website, but I still have to choose. Maybe I'll choose 10 number, first 10 people or any 10 people randomly who visit my website, and I'll ask some questions to them regarding their feedback. Okay, so that is a reservoir sample, right? So you do the sampling in any of these possible types. Okay, so anything you can apply, right? You do the sampling, right? Which is the best suitable sample, etc. Right? There are various methods to find out that, but as of now, not go to that level, and let's see. Okay, these are the options available. You can choose any one of them. Let's see. Right. So when I do a sampling and I have, okay, samples available, in or my what is my objective? What is my overall objective? I want to guess who is going to win, right? That is the decision of the whole population. The whole population means you may have 10 lakh people, but you are asking just say 100 people. Okay, whatever is the opinion that you get from these 100 people, right? You should be 100 people, in a sense, the samples, right? Out of those samples, you should be able to, you should gather so much information that you are able to guess the, or you are able to predict the actual result that corresponds to the 10 lakhs, the size of the population, right? So estimating the property of entire population by just using few samples, this is what is the major objective behind us. All right. So what you do, again, by just looking at there, everybody saying that okay, I voted A, I voted B, I voted A, I voted B. Using that, right, we try to get some of the properties of, right. We try to guess the population's property by using these answers. What you get. So the first property is called as a fraction. Okay, what is the fraction of something, right? I'll try to get this. So you see the example, right? How many vote will, right, candidate X gets? It's a portion. It's a fraction, right? 10%, 20%, 50%, etc. Right? So how many out of the visitors, right, to a particular website, how many will click the ad, because only when somebody clicks the ad, revenue is generated. How many will click the ad if Akshay Kumar is there in this? Okay, so you see, that's the plan, right? Aspirin will reduce the heart attack risk by what fraction, right? Out of 100 who take the medicine, right? What fraction, right? So same thing, right? Does covaxin reduces the hospitalization, right? So you will say yes by this percentage, this fraction ultimately. Okay, so one is the fraction, right? So our the discussion which we are going to start now, after say looking at the properties, will start from the fraction itself. So remember the word fraction. And the second major property is called as the mean, right? As in a general idea, we have the big picture of mean, what mean represents, right? So now our idea is that I need to go to the mean of the whole population by looking at the mean of the sample size. Okay, so this is the plan now. So examples are average height of children between 4 to 8, right? What you can do, maybe you may be able to visit 10 schools, hardly, right? So in 10 schools, 4 to 8 year students you may get, few colleges, few schools may have, right? So wherein again the whole class you will not do. You will look at the height of 2 to 3 students in a particular school. Like that you may visit say 10 schools. So 30, 35 or hardly 50 samples you may get. But you should be able to guess this for the whole city, let us say, right? So you see, right, the mean, what is the mean height, you may have to decide, right? Average volume of the milk in the packet, sealed package, right? Average expectancy of life in India is more than the South India, right? South Asia, or you can even compare it. So a life expectancy of North India is more than South India, yes or no, right? Like that. So this is based on the mean, right? So then average salary of men, women, you want to compare that. All these kind of questions will fall under the category where you deal with the property called as a mean of the samples, using which you need to guess the or the predict the mean value of the whole population. So two things are important we have defined. Okay, so the now actually we start the discussion about the what is called as the fraction part, right? So initial part is the fraction, then we'll go to the mean part. So in case of the fraction, so we took an example, right? Try to recall an election case, two candidate election, right? So denote one as X, other one as Y. Okay, so you can vote for X or you can vote for Y. There is no option like none of the above. So assume this is the case. So when you say I don't want X, which means you need to vote for Y only. There is no other option. Similarly, either I choose Y. If my option is not Y, then that means it is X. Okay, so probability of a voter choosing X is unknown. This is what our idea. I want to check that who is going to win, right? So to get that, right, for a whole constituency, if you want to guess that, maybe you will choose, right? You'll do a fraction. You will take the samples, right? Let us assume that the sample size is right 500, right? So I don't know the size of the whole population. Let's assume. So I am choosing 500 at random, out of which 320 of which they will say that yes, we have voted for X. Okay, so whenever you get this feedback from people, right, there are catches in that. Okay, we'll come to that at a later stage today. Okay, but as of now, let's assume that uh, everybody you asked, they told truth. Okay, saying that yes, I voted for this person X, and they actually have voted, let's say. So what we do, we can make an estimation, okay, that is P cap. So as you can see here, the P cap, okay, let me select a color to highlight. Yeah, so you see that this is the P cap, right? The P cap is equal to X divided by N. This as far as this problem is considered, I get 32 by 50, which is 0.64, right? Out of these 500, this is my this is the value, right? You can, it's a vote share, right? Out of 500 people I asked, 320, right, is the vote share. 320 by 500 is the vote share of candidate X. Okay, so this is straightforward. Now, can I make a decision based on this 500, right? This 500 people I asked. Okay, this particular, out of the whole population, this estimate P cap, right? Is it good? Now, so how good is this estimate, right? In the sense, I make a decision saying that, okay, 64% of vote is received by X. So can I say that X will win the election, right? So that's the first one. So in order to make a decision like for the whole constituency, I need the actual vote share, right? So you see the actual vote share is denoted by P. We don't have the value of that, right? Right. So that's one thing. Second thing, let's say that this P cap is close enough to make a decision. Yeah. No problem. Please go ahead. Okay. Yeah, sure. Okay. I'll repeat. Okay. So I have said 10 lakh people in the constituency. Okay. So out of 10 lakh, maybe 8 lakh people have voted for X, right? So that P which you calculate is the actual P. Okay. Actual P is actual value of vote share, right? But this P cap is corresponding to only the sample I took. I took only 500, right? Out of which only 320 told that I voted for X. So you see that is P cap. Okay, right? So I want to go for an estimate, right? I have an estimate P cap. Yes. No problem. No, we are not discussing the probability now. I'm looking at the vote share, the fraction. You look at this whole concept as a fraction, not a probability. We'll bring the probability concept at a later stage. Okay. P cap is the vote share in among the people you asked. I asked only 500, correct? Out of 500, 320 told that I voted for X. So that is the vote share of the samples. Okay, but actual vote share will be completely different, right? That will not be same 0.64 when you go for the 10 lakh people in the constituency. That will be different, right? Right? That is the P, actual value, right? So you see, right, I have a P cap with us. This is an estimate, right? From the samples, I get this estimate. But, right, in order to make an actual decision saying that, okay, candidate X will definitely win this election, you need this P, right? Only when you have P, and the P is more than certain value, you can say that yes, he is the winner. But I don't have that. I don't have a P, so that's the problem. We don't have this, right? I made an estimate by asking some people in my constituency. So in order to make a decision, this should be a good estimate, right? Now, what do you give? What do you mean by what do you mean by good? That's also is unknown actually. But anyway, for our understanding, let's say good in the sense if this is close enough, right? If the P cap and the P are close enough, right? Actual P is 0.8, and if your guess is 0.75, you can say yes, it is good. Okay, so something like that. So also it's the same thing mentioned in a different way. We need to know the difference between P and P cap. How close, right? The difference is smaller, they are close. So actual vote share is say maybe just 0.3, but out of the samples you made, you got 0.64. You see, it's too huge margin, right? So when you say he will win the election, but ultimately he will lose. See, right? So that's what is the difference is also going to matter. All right. So true. Yes, 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 yes. Perfect. Okay. All right. Now what we do, right? We'll bring the concept of what is called as a random variable. Right. So let's try to slightly modify this, right? The same problem we have, we'll try to write it in a different way. Okay. So that is, if we take many random samples with n equal to 500, what would be the distribution of p cap around p? So what do you mean by this? Now, initially I told that I'm going to ask 500 people in the constituency. Okay, that gives me one p cap. Okay, one p cap, single p cap we got, which is 0.64 as per the calculation. Right, now what we do, we'll modify this in the sense, I will ask 500 people again, not the same 500 people, different people, maybe a different region. Right, then also I'll get a p cap, different p cap than this. Correct, maybe you will get 0.55. So previously 0.64. Now I ask another 500 people, I'll get a different value, that is a different p cap. Like this, I keep on repeating. We take many random samples, 500 people from this region, 500 people from another region, then a third region, then fourth region, like n different times I'll try to repeat. Okay. So what happens every time I get a p cap? Will it be random? My question. This p cap will be constant always, or it is going to vary? It will vary, right? Because anyway, we know that. So as soon as I change the region, right, I'm going to get a different response. So that different response means, right, means what? It will be a different p cap. Okay, so you get a different answer. Okay, so this p cap, we will say that it is a random variable because it is going to take a random value. There is no fixed value. Some location, right, nobody wants that candidate. You will get just 0.05, let's say. In another place, everybody is supporting. So you get 0.99, let's say. Again, just guessing, right? Like that, you have complete variation possible. Starting from 0 till 1, you have various possible numbers that gets generated, real values getting generated because of repeating the experiment, right, over different regions. So we call it as a capital P cap, right? See the difference here. This P cap is a small letter. This P cap is a big letter. So look at the difference as well. In the previous slide, I'll just go back. So whenever we try to calculate this, right, you see this is the small letter p cap, which is small letter x divided by n, where small letter x is the number of candidates voted for x when you ask n number of people. N is fixed now, let us say it is 5. This p cap is the single possible value when I ask 500 people. Okay, but when I repeat this many times, this is what is going to happen. I may get n number of p cap values, small p cap, small p1, small p2, small p3 cap, like that. Depends on the number of people you ask. Okay, so you ask many people, right? And when you ask many people, like in one region out of 500, few of them will say yes. Okay, few of them will say yes. So that means, right, the p cap is going to be a random variable. Okay, so the capital P cap is the set of all the small p caps you get. How do you obtain that? That is again by using a equation, same equation, x by n, where this x is a variable now. In one constituency, 320 told that, in one region, 320 told that I voted for. In a different region, when you ask another set of 500 people, they may say that 550 people might tell that I voted for X. In a different scenario, just 100 people will tell that I voted for candidate X. So this is that random number, right? You get to see that people think, yes, I voted for X. N is fixed 500, but this X is a random number. So because of X being a random number, my P cap is also going to be a random number. I hope that is clear. Right. So same thing has been mentioned in the the 2 points mentioned here. Right. So since it is a yes or no type of situation, so X is a random variable which denotes number of success, number of people voting for X. I consider that as a success. So which variable it is? It is a binomial random variable. Okay. So S no type, always binomial. We already have this. So now what we do, we'll bring the concept called as an estimator. So this is a random variable, right? The P cap, whatever I generate, is going to be a randomly distributed, right? So let's look at the properties of a random variable. So what are the properties? For any given binomial, the mean notation is capital E of that. Okay, E of whatever is the variable. In this case, P cap is my random variable. So expectation is denoted by capital E, that is a mean. Mean and expectation are same. Okay, we'll discuss this in probability when we go to that particular model. So it's a standard, I get P. In the sense, so we are coming closer to the answer step by step. So I know that the P cap is randomly is a random variable and it's distributed in a binomial fashion. Okay, so P cap here, P cap here, P cap here. Every P cap I get. P cap may be different values starting from 0 to 1. Obviously, it is known. Somewhere you may get 0.15, 0.35, 0.55, 0.64, 0.75, etc. You see all these variables, if you plot, it becomes a binomial distribution. Okay, so this binomial distribution has a very peculiar feature. We just have calculated that mean of the P caps is what? Mean of the P cap itself is the actual P. So I wanted the actual P, right? So this is giving you some hint. Okay, yes, you can calculate the P, right? If you know the P caps, many key P caps you have, you can take the average, you can come closer to that. First thing. And what is the variance, right? I can even calculate the variance of using those P caps. I can calculate that. So variance, whatever you obtain for that P cap, right? That will be P into 1 minus P by N. Okay. I don't know P, but still it's giving you some hint. Okay. You have a P caps, several P caps available with you. Calculate the mean of that, that will become P. Calculate the variance. It is also represented in terms of P into 1 minus P divided by N, where N is known to you. That means the standard deviation is root of variance, root of P into 1 minus P divided by N. Okay, so I may be able to reach the P from P cap itself. First hint. Okay, this may not be very clear right now. Don't worry, hold on. So just understand that, okay, there is some relationship. I repeated my experiment to calculate the P caps again and again. That means I'm coming closer to P because there are equations using which I can go to P, right, using the P cap. All right, that's the hint here. Nothing to worry about the equation, how we got the equation, don't worry, absolutely fine. Again, there is a thumb rule, right, which actually proves that you repeat any experiment for a large number of times. Okay, it's called as a central limit theorem. According to that, you repeat any experiment. It doesn't matter which is actually distributed binomial or any other one. Okay, when you repeat that n number of times, as you increase the number of samples, right, irrespective of what is the original distribution, finally you are going to get the normal distribution. So you say it is normally distributed if at all you are going to repeat this larger number of times. Okay, as the population size increases or as the sample size increases, this tends to be a normally distributed. So now you understand why we concentrated more on the normal distribution when we discussed about the probability distribution. It is just because as I increase, everything will become normal. First point. And the second is we are going to deal with the big data, right? So big data means huge data set. Huge data set means huge number of samples. Once again, if you calculate a probability, that should look like normal. So others, we just got introduced other types of distribution and we concentrated more on normal. for this reason. Okay, everything try to think whatever we have done so far is making sense. All right, let's proceed further. Next point is that so the p cap is centered around p, right? So p is the mean somewhere here. The p cap will be distributed around this center. So p caps on the right side, p caps on the left side, and it is which distribution? It is the normal distribution. So try to recall the graph. Center you have highest value, surrounding that you have many other values. Okay, so what is the spread, right? That is proportional to the 1 by root n. Everything, all the parameters which we know, we are trying to relate that to the normally distributed curve. Okay, what is the significance? We'll come to that. So we'll change the vote share, let us assume, right? Let us assume that the actual value of P is 0.66. I guessed that by asking few people in a region, 500 people I asked, they told 320, right? 320 of them told yes. So what I got, right? I got to know that P cap was 0.64. Let us assume when you consider the whole constituency, right? Actual vote share is 0.66, right? You see, this is the 0.66. Right, how I come to know this only, actually I will come to know this only after the declaration of the results. Okay, but let's assume, right, I know that P is equal to 0.66, which is the actual value. I don't know this yet, right? But let's say that vote share of the total constituency is 0.66. Now, so using this, I can actually calculate, use this equation. So the standard deviation can be calculated as sigma p cap is p into 1 minus p divided by n, right? So apply the same thing. So p is how much? P is 0.66. Okay, 1 minus p is 0.34. 1 minus 0.66 is 0.34 divided by the sample size. Sample size is how much? 5. So that means this is 0.0212, right? So the idea is that you can expect the p cap to follow the normal distribution with the mean value 0.66 and the standard deviation being, right, 0.0212. But this is valid, right? When I calculate a capital P cap, it is valid only if you know the P, right? But as of now, this is just, I said that, okay, assume that you know, but right now we don't, right? So we have to we have to find out a method, right? Either you calculate the P from the P cap. That's the first thing. Normally it is not possible because you are doing a very small cell, right? Population size is small, right? Population size you can keep on increasing, but ideally in order to reach the actual P, you should ask everybody. Once you get that, okay, then you say yes, this is the answer. But that's not going to happen, right? So that option is ruled out. But you see the last point, for this we need the value of P. As of now, we don't have P. Okay, so I hope things are clear as of now. This part is already we have come across once, but still I'm trying to make you to recall, right? So now the next approach will be, will you be able to get the P from P cap? If not, right, what are the alternatives, right? What are the various calculations that you can bring in so that your P cap comes as much closer as possible to the P? You may not get the P, but can you make it as much closer as possible to P so that sorry, the prediction that you're going to make, right, is close enough to tell that, okay, I predict that this person is going to win the election, right? Like that. Otherwise, when you talk about the country, you maybe it's something like this party is going to win this election with these many winning in these many constitutions, right? So 350 out of 545, like that. So that's what we are expecting. Okay, will you be able to make that decision ultimately, right? How do people make? So you see that the exit polls will come, right, after the election gets over, right? Various channels will display something like, okay, this part is going to get 260 to 380, right? Some number will come there. How do they display that? We are going to come to that ultimately. Okay, right. So we need to bring few more concepts over here. So far, whatever we were discussing, it falls under a reasoning part. I'm trying to give reasons, right? That actually falls under what is called as a deductive reasoning, right? So basically deals with the sampling distribution. You have a larger population. I keep sampling them like 500. I repeat. Okay, so trying to estimate the parameters. Normally we go with the fraction, mean, etc. Right? From that, I'm trying to obtain a distribution. So far what we did is the same thing. Okay, so trying to get a distribution out of it, right, by repeating the experiment again and again. So there is another version of the reasoning, right? This is uh, this is a way where I don't repeat my experiment. I do only once. Let us say, start from one set of observation. I just talk to 500 people, right? That's the starting point. Start from one set of observation. So once I have, once I finish that, right, I'm supposed to investigate, right? I'm supposed to come to a conclusion. Before that, I need to do the maths and all. So I'll call it as an investigation, right? That what can I conclude about the whole system which generated this data? In the sense, these 500 people whom I asked, right, they are a part of the whole constituency, right? What can I conclude about the whole constituency by just looking at this, right? This is the inductive part. Induction, right? Mathematical induction, maybe you have studied somewhere. Okay, those who have studied mathematics, like PU level or before that, maybe you have come across that. Okay, so it's an inductive part. You start from a small part and then you branch and cover up the wide region of your space, right? So that's what is induction. Starting from a very small point, keep growing, right? Yeah, we'll be coming to the examples. Okay, yeah. So yeah, so time for a quiz, just to check that what you have understood so far. Okay, I'll try to generate. I'll try to generate a quiz, maybe. Okay, let's see. Okay, just hold on, please don't answer. I'll bring up a this thing. Okay. Okay, just hold on. Just hold on. This is quiz. Okay. Maybe I'll just bring a quiz number one. Okay. Yeah. So yeah, here we go. I hope everybody can see quiz one as a poll on your screen, right? So please select the choice over there. Okay, you can see that less than 50% participation, right? I want everyone to participate in the quiz. Okay, this gives me an idea that what percentage of you have understood, right? So what pace I should go, etc. I will be able to decide by looking at this. Okay, so requesting everybody to participate. Right, Swapnil, please go through the quiz questions and select it on your screen. Okay, don't post it over here. I'll discuss the answer immediately afterwards. Okay, yeah. Okay, I'll give 30 more seconds. Uh, Only 16 out of 25 participated so far. Okay, others, please. Yes. Okay. So there is a 75% of participation. That's good. I'll end the poll, right? So, right, you can see the results now. I think results are being shared with you. Okay, how many people, what's the percentage of votes people have chosen which choice, etc. You can see there. All right, now, so the first question, right, a random variable of estimated vote share, right, is going to follow, right? It's a vote share, right? So yes or no type. So the answer is binomial. Okay, and coming to the standard deviation is the root of the variance. So if you look at the variance part, right, so let me go back, right, say this, the variance is p into 1 minus p by n, standard deviation will be a root of that. Okay, so you need to answer the one which has a root, right? So p into 1 minus p by n under root is the correct answer. Okay, I hope things are clear, right? Try to recall, right? And so we had a problem here, right? So in the previous case, this is where we actually had stopped, right? I don't know the value of p, right? So I need alternatives so that using the p cap, I come closer to the p value, right? So for which the one solution is called as the confidence interval. Okay, so confidence interval, in the sense, I should be confident about, I bring a concept called confidence, which actually tells, okay, I'm so much confident about my guess. So how to bring that? That's what we are going to discuss. So we are in the same situation. So let's take a sample size of 1000. So people in favor of the one of the candidate is 550. So take up a fraction. So 550 by 1000 gives you 0.55. Right. So this is what already has been discussed, right? I'm trying to push you harder so that you don't forget anything. So this is again related to only 1000 people, but I may have 10 lakh people. I want to guess that. So what is the guarantee that the estimate I just made, that is P cap, is the correct one? You see this 0.55, it's actually at the very border. 0.5 is proper border, it's 0.55. It may jump to the other side, right? When you take the whole average or whole fraction of the constituency, right, it may go to the other side. There is a big chance, right? So what is the guarantee that whatever you guessed so far is right, correct, right? At least, now you see the other point which I just mentioned, right? We are mentioning at least what is the guarantee that the real value of P, right, won't be less than 0.5. What happens in that case? Whatever guess you may declare that okay, the person according to 1,000 people's opinion, A is the winner, right? But what's the guarantee that when you consider all 10 lakh people, it's not going below 0.5? Because somebody, if you get a fraction less than 0.5, it means you are a loser, right? So that person will be a loser. So you guess that it is more than 0.5, but at least you may not be able to tell specifically that this is the final value of P. No, not audible, Niranjan. Can you repeat? Not understanding. Can you type, please? Audio is not clear. Previous slide. Okay, okay. Yeah. All right. Fine. So, yeah. So this is the idea, right? At least you should be make sure that, right? Whatever I guessed, it may not be a proper one. I just guessed that 0.5 or 0.55. Actual value may be 0.6, 0.65, right? But at least make sure that whatever you say as a PCAP, right, will not fall on the other side. Results will not be changed when you consider the whole population. So that is what is the ultimate point. So to do that, one step we go ahead, right? We enter into a concept called as confidence interval. So how to bring that, we'll see. Okay, so intuitively we'll try to get introduced to the what is called as the confidence, right? So let us consider, everybody knows Deepika Kumar, right? So, right, whenever she hits a target, right, so it is observed that, right, 95% of the time she is going to hit the bull eye. Bull eye means that's the center of the innermost circle, right? So that region is what you call as the bullseye, right? So those who hits there, you get a highest point, right? Pointing count of the point will be happening according to that, right? So let us say, right, there is an innermost small region of the circle, right? In the yellow region, right? Again, you open up any other bigger pictures to visualize this clearly. I just have pasted a small copy. Okay. So at the center, right, there is a 10 centimeter radius of the bull's eye. Within that, she will hit 95% of the time. Let us assume. In the sense, if she fires 100 times, 95 times, arrow is going to hit this region. Okay, so hope the point is clear, right? Within wherever she is supposed to hit, she will hit 95% of the time. Okay, now I'm trying to convert this concept into the confidence, right? The confidence comes now, but so the first point should be very clear. She's going to hit 100 arrows, out of which 95 of them will hit the 10 centimeter radius around the bullseye. Bullseye is the center. Around that, a small circle is there. Within that, you need to hit. Okay, fine. So, under this situation, now in order to bring the concept of confidence, what I do, right, I will move behind the target board. So far, we were looking at here, there are markings. So, arrows will come and hit from this side. Okay, so there is a central region, bullseye. 95% of the time that will hit over there, corresponding to this. Okay, now I go, I'm going to the backside. So backside means, right, in the slide you can see there is a blank region on the, right? So you can see that. So this is the one which I'm talking about. Okay, this is the backside. Right. I'm moving backside now. So, and over here, every time she is going to hit, I'm going to mark that region. I understand that. Okay, I'll be able to see that. Okay, it's hitting this point now, here, now. Next, it hits here, it hits here, it hits here, like that. I have various points. Okay, the points I'm observing this from the back side. Okay, so from the back side, I'm looking. So point should be clear. So that's the second point. Let's sit behind the target, right? So bullseye is not centered on the board. Bullseye may be anywhere. Doesn't, I don't know, because I'm sitting on the, so right. So this is a portion of that board, right? Bullseye may be present anywhere. I have no idea, but I can see that arrow hits here, arrow penetrates the board, and arrow's head will come to the other side. So I am able to look at the point, right? So where arrow is hitting right now. Okay, so I hope that is clear to you. All right, so I will mark some of the points. Okay, let me change the color so that it becomes visible. So initially arrow hits here, then the arrow hits here, then the arrow hits here. Some of them let me mark. Okay, like this. Right, so arrow hits at all these green dots. We are able to see that, okay, arrow hits here. Now, so look at the previous idea, the first diagram, which is on the left side. Actually, you can see the target board, and at the very center, there is a bullseye. Surrounding that, you have a 10 centimeter radius. So that is the region which you are supposed to hit. Now, what I do, arrow hits at this green, right? So draw a 10 centimeters radius, 10 centimeter circle around each one of them. This is my point. Okay. Why I am doing exactly 10, I will come to that. Right? I have a point. I can see only the point because I'm sitting behind. So around a point, I'll draw, right, a circle. Circle of specific 10 centimeters. Repeat. I have, say, as of now, I may see 5 dots where the arrows are being hit. I'll draw 10 centimeter circle around each of them. Keeping that dot as a center, draw 10 centimeter circles. So some of the circles, what you can see here, right, I have just drawn. Okay, now, so the idea is that circles will contain the bullseye 95% of the time. Can I make that statement? Because you look at the first statement we made. Whenever she actually hits the arrow, right, 95% of the time, it will contain the bullseye. It will hit the bullseye, which means any point you hit, draw a circle, right? So that should contain the point which you are supposed to hit, right? So that's why we make this statement. This circle, the circles which you are drawing now, right, without knowing where is the bullseye, you are sitting on the backside and you are doing something, right? So that circle will contain, right, the bullseye 95% of the time. Now you see, this is the confidence. So let's try to make it in a different way, right? Draw 10 centimeter circle for every shot of Deepika, right? 95% of the time, that circle which you are drawing will contain the bullseye, right? Now I am confident, right? So I observed something and I'm trying to bring the concept of confidence. So this is just an intuition, right? Nothing to do with our example. I will come to the example at a later stage. Okay, so if at all I want to show you, right, I'll change to a different color. So let me assume that this is the bullseye, whatever you are seeing here at the center, let me assume, right? So you see the statement written over there, right? Any circle you draw, 95% chance is there that it will contain the bullseye. Okay, so are you getting something, right? Yeah, we are open for questions. Any doubt you have, please ask. All right, so we'll move ahead. So see, now the diagram actually I have changed, right? Wherein you can see that, right, the various green dots may not contain, right? May not be the actual point which is supposed to do. But the orange color dot is the actual, right, bullseye. Now you see 95% of the time, the you draw the circles, right? 95% of the time, right, this orange dot is present inside the circle. 95 circles out of 100 circles will contain this particular dot. Okay, so that is what is the intuition, right, we are trying to apply here. Okay, let's move ahead. now we are coming back to the mathematics behind this. So how do we understand, or how do we write the maths? Right, so what is a random variable here? So try to recall the p cap. The capital P cap is the random variable. All right, so that means already we have calculated this. This is a random variable, the p cap. It is actually, it's a normally distributed, because you are repeating the experiment for a large number of times. It has a mean value that is equal to p, and it has a standard deviation denoted by this. Okay, I hope this is very clear. Now you have a distribution, means can you convert that into z? What is this z? Try to recall the normal distribution, right? So I have any normal distribution, I will convert that into the standard normal distribution. How do you do that? So you have a mean, so x minus mean divided by sigma. This is what I am supposed to do, right? That is what I am going to call it as a z. So, right? So try to recall that. I'll give just say 5 minutes or 5 seconds of time just for you to think what is this z, right? So the name says that, okay, applying z transform standard table, nothing to worry, simple, right? So I have a normal distribution. In order to do the manual calculation, I need to shift it to the center so that mean lies along the y-axis, or mean becomes 0, standard, so sigma becomes equal to 1. Okay, so we are trying to, right, do this with respect to this random variable p cap. Okay, so I'm confident now. Let me bring the confidence applicable to our problem at a later stage, but just doing the maths now. So convert this, whatever distribution you have, bring it to the center, right? By converting whatever variable it is, you convert that into the z, right? My x-axis should become z. Okay, so I hope that is clear. Like what you are going to do, I am supposed to perform a transform. The word z transform here, because right now I have p cap along the x-axis. So the p cap needs to be converted into the z. So how do you do that? X minus mu by sigma was there. Now I will do p cap minus the mean divided by sigma. But what is mean? Mean is equal to, see, I want to come to this, right? See the equation. I'll come to the left hand side later, don't worry. So why I'm writing 0.95, I'll come to that. Okay, so what are these values? 1.96, how you get everything I'll answer. Don't worry about that now. So there is a minimum value, there is a maximum value. In order to get 95% confidence saying that yes, my approximation is right, my p cap is correct, right? My p cap is close to p, right? In order to do that, right? Again, I have some normal distribution. I want to convert that into the standard distribution. So standard means you have to perform an operation denoted by this part. What is that? Saying p cap minus p divided by standard deviation of p cap. Recall. So previously we did x minus mu by sigma, where mu is the mean of x and sigma was the standard deviation of the x. Now we don't have x, now we have p cap, so everything is with respect to p cap, that's all. So just look at this equation. I hope you are comfortable. Okay, now I will come to the other terms. So I am supposed to write in terms of z, right? How I wrote z? I just wrote this part. Okay, fine. Now in case of a z, right, if I integrate between any two values, what do you get? You get the probability, right? So now I say that I'm 95% confident means probability of the person winning should be 95%. In the sense, because of my prediction, right? I should be able to be in a position that I should be able to make a statement that, okay, my result or sorry, my prediction is 95% correct. What do you mean by that? That's a probability, correct? So confidence is actually in some way it is a probability. So what I do, I'll put that on the left side or put it on the right side, doesn't matter. So something equal to 0.95. What is that something? Area under the curve should be, right, 0.95. I know that the total area is 1, right? If you are able to make a proper P cap, which is surrounding to your actual P, right? So where should be my P cap is what I'm trying to guess, okay? Because there is a problem if I guess the P cap as 0.55 and results turn out and you actual value of P is 0.45, candidate will lose. So that should not happen. That's my idea. So I should be able to guess the P cap in such a way that is closer to this. So not just closer to the actual answer, I'll try to make a confidence level coming into picture. The P cap's position is such a way that my results, I'm confident that my result is 95%. Whatever I'm guessing is 95% correct. So I'm writing the value 0.95 over there, which is the probability that is resulting because of my guess. Okay, so 0.95 is clear because I'm saying that I want to guess the P cap in such a way that my result should be 95% correct. So that's my confidence level which I define. Okay, coming to the 1.96 and minus 1.96. Can anybody tell what it is? You already have, we have solved so many problems in the normal distribution. So it is just related to the normal distribution only. Okay, nothing outside, nothing new, right? So I'm asking the question. Yeah, we are open for oral answers as well. Yeah, so if you are able to answer that, that's well and good. Okay, so take your time. Anybody? You think you open the standard normal table? Okay. Maximum and minimum numbers. Which number? Maximum, minimum is right, but what are the numbers? Yeah, okay, okay. Yeah, so how did you decide is my question. How can I say that like 1.96? I can say 2.5. I can say any other number. So, right? I'm trying to get that answer. Yeah, you are close enough. The answer is whatever you get is actually right. Right? You say that this is the minimum value of z. The other one is maximum value of z. So that what? Why the specific 1.96 is my question. Hmm. Yes, yes, yes. Please proceed. Hmm. Yes. So there is a, see, when I say 95% accuracy I want, that corresponds to 5% error, right? So yes, in both ways you can think of, right? And corresponding to that on a standard normal table, 95%, right? In a sense, if you consider a table like this, what's the total area is what I'm supposed to find out. So total area I'm supposed to find out is 0.95. So on the right side, 90.95 by 2. Correct. So that's the area that should be present on the right side. So if you have normal table, please open that up, right? Which value of Z gives you the value equal to 0.95 by 2, right? That Z is 1.96. Okay. On the right side, I have 1.96. Even on the left hand side, I should have the same value to get the same area because the curve is symmetric. Hope it makes sense. Recall the problems we have done so far. All right. So whenever I want to calculate the area between minus Z1 to plus Z1, you just consider 0 to Z1 multiplied by 2. Okay. So that multiplied by 2 gives you 0.95, means actual Z is, right, divided by 2. Right. So corresponding to 0.95 by 2, whatever Z value you have on the table, you will do the reverse calculation. Okay. You look for, right, inside the table, look for a value which gives you 0.95 by 2. Okay. That value, read the Z, right, either here and here on the top. That is nothing but 1.9 like vertical, 0.06 on the top. That gives you the exact value. That means my Z value is 1.96. For 95% confidence, if you want, right, I am supposed to consider the width of the interval, right? That should be 1.96. So which means the Z which you calculated, right? Because of you had a P cap, you have a P, you have a sigma of P cap. Using all of them, I calculated a Z. If this Z lies between minus 1.96 and plus 1.96, that means yes, your answer is 95% closer to the right answer. Any doubt? Any doubt with this statement? We'll do the maths now, okay? But before that, before doing that, right, this is my statement, right? I had a P cap, I have a P, right? Yeah, so you can see Gaurav says that the value of 1.96 in the table is 0.475. What is 0.475 into 2? 0.475 into 2 is 0.95. Correct? So 95% I want, out of which half of the area will be on the right side. That means I divide by 2, so 0.475. Look at the table, where is 0.475? Read the values, right? You will get 1.96. So I am doing the reverse. Previously in the problems, mostly we used to do, I have, sorry, I have 1.96, I read 1.9, I did 0.06, I get a, right? This is what we do. Now I am going backward. I know that I need 95% confidence in my result. So what I'm supposed to do, I split the area into two pieces. I get 0.475. Corresponding to that, what is the Z value that you read? That will be 1.96. So Z1 to minus Z1 you need to consider so that it is symmetric. So my values are, right? So I'm looking at the second equation, minus 1.96 and plus 1.96. Okay, that's fine, but I still have no clue about P, correct? Where the P lies. I want to calculate the P, right? Because as I earlier mentioned, I may not be able to guess the exact value of P because of this P cap. But definitely my intention is to come as much closer as possible to P. At least I should get a range saying that, okay, P may be between this to this. That is what is the numbers displayed in on a TV when they do the exit poll, saying that you get a vote from, you get a seats from this number to this number. So there is a variation, right? There is a minimum, there is a maximum, right? So that's what we are trying to discuss now. We are coming to that point at a later stage, but still, right? So I still have a Z. My Z value should be between these two, so that I can say with 95% confidence, I can say that yes, my result is close enough. Okay, so look at the equation number 2, right? I'm going to use this equation here. Okay, now simply I can convert this equation, I can modify, simply do the math so that this I can convert this into AP. Okay, so let's do that now. Let me try to do that for you. Okay, I'll do the maths. So I have written the answers over there, but I think it may not be clear to everyone. So I'll try to do the maths. Okay, just 2-3 steps we'll get to that. Okay, I hope everybody can see the writing pad connected here. Okay, all right, all right. So, right. So this is the equation. Right, I'll write the equation here. Okay, so okay, so the equation what we had the second equation which I mentioned just now, right? I'm writing that itself over here. Okay, so the second equation says that 0.95 on the left hand side. This is approximately equal to the probability that minus 1.96 is lesser than or equal to the z value, which is also lesser than or equal to 1.96. Hope this is clear, right? The z means I will replace 0.95 is approximately equal to the probability that minus 1.96 is lesser than or equal to. How did you get the z? By performing the, by using the random variable p cap minus its mean, right? Mean of that is small p, divide that, right, by sigma of p cap. Okay, this should be lesser than or equal to 1.96. So these two equations I already have. Now I'll do the mathematics. So what I do is, right, so only this part you consider. Okay, only whatever is inside this bracket, right, we'll try to consider that. So I'll multiply the sigma p cap to both sides. There are actually two equations. One is minus 1.96 less than equal to something. That's the first part of the equation. Okay, first part of the equation I'll try to highlight with the say red color. So my equation number 1 is actually this part. This is one equation. I have another equation which is on the right side. You can see that this is my second equation. Right? There are two equal to signs. So it's written in a same line, but there are two parts. Okay, so considering that, let me try to modify this. Okay, so anyway, I'll try to finish this quickly so that everybody can take a break. Okay, right. So this is only that part. Whatever I highlighted is in the bracket. I'm trying to write that now. So there is a 0.95 on the left side. P is present over there. Don't worry. Okay, it's still there. I'll multiply the sigma p to the both sides. So that becomes minus 1.96 into sigma of p cap should be less than or equal to the capital P cap minus P, right? Should be lesser than or equal to 1.96 times sigma of P cap. Since there are two equations, I have to, okay? All right. Now, I'll take the P cap to the other side. So P cap, which is at the central part of my equation, this equation, from that I'll take the P cap to other side. I have to do this on both sides. Okay, so that means what? That is, so minus P cap minus 1.96 sigma P cap should be lesser than or equal to minus P should be lesser than or equal to minus, oh, it's capital P cap, sorry, let's correct that. So this is minus P cap, then we have a plus, right, 1.96 sigma P cap. Okay, so simple mathematics. Now what I'm trying to do, I'm trying to change the sign. You see what is there at the center? It's a P, right? I'm getting a range of P now, but it is on the negative side. It's a minus P. I want a plus P. So what I do, I'll change the sign, right? When you change the sign, very important, the wherever you have, if you have equal to, it remains equal to, no change. But if it is less than becomes greater than. Okay, if you have a less than equal to sign, that will change to greater than equal to. If you have a greater than or equal to, it changes to less than or equal. So basic mathematics I'm applying. I'm trying to make you to recall this point. So because of what I'm trying to write this now. So sign changes. Again, the inequality will also change. That means sign change, that is P cap plus 1.96 P sigma P cap. My mistake, sorry. 1.96 sigma P cap. You see the sign change. So there is a less than. This changes to greater than or equal. Okay, minus P becomes plus P. Less than becomes greater than or equal to. Sign change once again. Okay, so that is P cap minus 1.96 sigma P cap. Sorry, I'll rewrite the last part. Okay, so this is sigma of P cap. So remember this equation. I should rewrite this. The rightmost is the smallest one, that should come to the lowest part. So that is P cap minus 1.96 sigma of P cap should be lesser than or equal to P, should be lesser than or equal to the leftmost term. I'll move it to the right. P cap plus 1.96 sigma P cap. Right. So you see, P cap is known to me. Sigma P cap is also known to me. That's it. If I know that, I can definitely guess this, right? What is the range of P? It is not an exact value, but you see that this is what is the range. Now I write the complete equation. Left hand side there is a 0.95. That is equal to, there is a probability of this. Okay, just look at this equation, right? Keep looking. I'll change my screen so that you will get the same thing printed over there. Look at the last equation. 0.95 is approximately equal to probability of P cap minus 1.96 sigma P cap lesser than or equal to P, lesser than or equal to P cap plus 1.96 sigma of P cap. All right. So that is how we got into this equation. That is the last equation over there. Okay. All right. So is there any doubt? Okay, I hope things are clear, right? Anyway, we'll take a quick tea break, and we'll come back and we'll continue. Welcome back. Okay, sorry about that. I think a few of you couldn't identify that I mentioned the break. Sorry about that. I think I should have written again. So I hope everyone is back, and we are open for questions. If you have any question, please feel free to ask. I think you are fine with this part, right? So, right, we are cross multiplying the denominator to both sides. We get this equation. Okay, that is obtained by cross multiplication. Denominator will move to the other side numerator. So that is happening on both the sides. And I'm taking this positive P cap to the other side. On both the sides, I'm going to move it so that it becomes negative P cap. So that's what is happening here. You see minus P cap, remaining terms are as it is. So I get a minus P cap on both the sides, right? So whatever P cap was here, it's being moved to the right, this side as well as the other side. It becomes minus. Okay, then I want to write a P, right? I have a minus P in my equation. Since P is actually, right, expected to be a positive number, positive real number, right? We try to convert that into positive. When you do so, right, all the sign will change because minus P is expected to become plus P. During that, all the sign will change. Minus P becomes plus P, minus 1.96 sigma P cap becomes plus 1.96 sigma P cap. Same thing happens even on this side. Okay, so here you can see minus P cap becoming plus and plus 1.96 sigma becoming equal to minus 1.96 sigma. Okay, so I can simply replace this whole equation, right, by this equation. So that's what you see as the last answer. 0.95 equal to probability of this. Okay, I hope that is clear. Any other doubt? Okay, where is the extra P? There's no extra P. I'll show it again. Yeah, you see here, I actually have left a P here. Sorry, there is a P here, right? So that is not present. I'm going to put this back, right, over here. Probability of, okay, probability of this should be 0.95. Okay, sure. Okay, I hope everyone is back and we'll resume, right? This mathematics is not yet over, right? We'll proceed. Okay. So, okay, so yeah. So we obtained this last line. So there is a meaning to that. So what is the meaning you see here, right? In terms of a deviation, the Z takes a certain value, right? Z has a mean and Z has some standard deviation on both sides. Center is how much? Center is 0 because it is standard normal distribution. We converted some normal distribution into standard. So standard means from the center, you have so much of deviation. What is the deviation on to the right side? 1.96. Why it is 1.96? You have the answer. Okay. So if at all you are trying to relate this to the previous example, right? The bull's eye problem, right? Arrow hitting the bull's eye, 95% confidence, right? So that is right modeled using this particular concept. Okay, if at all you try to convert that into a Z, and if the Z lies between minus 1.96 and plus 1.96, means right the radius of, so I hit a point, so I draw a 10 centimeter radius circle, so I am 95% confidence that, right, I'm 95% confident that, right, this radius of the bull's eye is 1.96 standard deviation. Means 95% confidence means in terms of mathematical words, I can put it in this way. Radius of the bull's eye is 1.96 standard deviation. Okay, it's a mathematical sense, that's all. So my point is still same. I take a point, I draw 10 centimeters the radius circle, right, from that point, keeping that point as a center of the circle. What is the meaning? The meaning is that there is 95% chance that your the bullseye is present over there. So that is told in a different way like this. Okay, can be written in a different fashion. You see here, right, corresponding to this equation. So 1, 2, the third equation. This equation can be mathematically, right, written in this way. The current strike, whichever the arrow hits, whichever point the arrow hits on that particular target board, right? Current strike is plus or minus 1.96 intervals, right? With 95% chance. Okay, just a mathematical sentence is like that. Okay, if I want to translate the given what you call given equation, this is the given equation, I want to convert that into a sentence, means this is how you put the words. This is mathematical means all refers to the same point. Okay, so look at the last one. Bull's eye, that's the last equation. Bull's eye is 95% inside that interval with plus or minus 1.96. Okay, so that's the mean. Okay, so with interval in a sense from the center, how much you deviate, right? So it's a standard deviation. Okay, all right, let's move ahead. Little bit of maths is left over. So now, because of all these calculations we have made, right, now you see that, do you know the sigma of p cap, right? We don't know that, but it depends upon p, correct? So what we do, we don't know that value directly. We cannot calculate that because if you look at the equation, it depends on the p value. Since you don't have a p, we cannot calculate. Okay, so still I have an equation, but still it's not going to give me the expected answer, right? I wanted to go closer to p. I have a term which is sigma p cap, right? look at this equation. The sigma p cap equation, if you see, it is nothing but p into 1 minus p by n, right? Since it is p minus 1 by p by n and I don't have a p, I cannot still go to this, right? So for that, we introduce a term, okay? We introduce a term that is called as a standard error. Okay, how do you define the standard error? Look at this equation. Standard error is denoted as SE. So instead of that sigma p cap, which I cannot calculate, if you have a p, yes, I have an equation, I can substitute and I can calculate. But the problem, I know that I cannot go with that equation. I don't have it. So instead of that, we introduce a similar term, right, which can be calculated using the p cap itself. Because I know that the p cap is in the vicinity of the p. It follows a distribution. It has a certain, the mean is equal to p, which means it is bounded to the p itself. P cap is bounded to p. I can make that statement, right? No problem with that. So since I don't know p and I know p cap, I can put p cap in that equation, but it's not going to give you the sigma p cap. We will call whatever we get after substituting here. You see the difference here. This equation is different than what we already have used because it is not p being substituted here. It is a p cap. Correct? Look at the equation. Sigma of p cap, standard deviation is nothing but under root p into 1 minus p by n. P is not known. I cannot do that. So I will substitute p cap over there. And whatever result is obtained, we will call that as a standard error. That term is called as standard error. Okay, so now what we do, I don't know sigma p cap, right? I will update my equation. Since I cannot calculate that, I will put standard error of p cap. So since the distribution remains same, right, the result will not be altered by a huge margin. There is small effect. Okay, there is a small effect because I am not substituting sigma p cap. I am substituting another variable, another value, which is calculated using p cap, and that term is SE of p cap. Okay, I'm substituting a different value, so there is a difference. So this is approximately equal to, like, right? This is not exactly matching. There is a difference, but approximate. Anyway, we are always, since the beginning only, we are doing an approximation only, right? I'm calculating a fraction, using the fractions to do some calculation, etc. You see, everything is approximation only. So this also, people have done research behind this mathematics. Okay, it's not simply calculated and substituted. They have a valid reason saying that even though you cannot calculate the sigma p cap, you calculate a standard error and put it over there. Okay, still it is going to work. Okay, so this is the only solution we have because we have only p cap with us, right? So using the p cap, right, if you update your equation, you see only this term is changed. This was sigma p cap, right? Even on the other side, on the right hand side also, we had a sigma p cap. Replace that by SE of p cap. How do you calculate SE? P cap into 1 minus p cap divided by n, everything under root. Okay, so update your equation. So last line, you look at the last statement. Okay, so it says that the true population fraction, see, we are looking at the fraction only, right? For the complete constituency, I am supposed to calculate a p, right? That p is nothing but a fraction. So the true fraction of the population lies or falls in the interval, right? P cap plus or minus 1.96 times standard error of p cap with 95% confidence. Now you can say that, okay, if I know a p cap, right? But remember, you need to have, you should have done this experiment several times. Okay, so capital P cap is what we are talking about, not the small p cap. Small p cap is only one observation out of 500 people. But if you repeat this many times, I get a capital P cap. So capital P cap plus or minus 1.96 standard error corresponding to this P cap, right, will give you a, right, 95% chance that your actual result is within this range, right? P cap minus something, P cap plus something. Within this, you have the P, right, with the 95% chance. Okay, 95% confidence. We don't call it as a chance because already we have brought up 1.96 specifically for 95% confidence. Okay, yeah, we are open for questions. Any question? Okay, so let's proceed further, right? So now we'll do a small mathematical example. We'll try to solve. Okay, so now you see, right? It's the same problem of getting into the election results, guessing that what's going to happen. Consider sample size of 1000 out of 500. Sorry, out of 1000 people, which right, I tried to contact and talk about the election, right? So 550 of them say that they have voted for candidate A, right? So what is the fraction of this particular sample I obtained is 0.55, right? So from that I can directly calculate the standard error, right? So previous steps, whichever we did, right now we are not going to that because, right, we have updated, right? Whatever is the calculation we are going to do, we update it through several set of equations in the previous slides. So what we do, we calculate the standard error of P cap. What is that? P cap into 1 minus P cap divided by N. So under root. So under root P cap 0.55, 1 minus P cap is 0.45 divided by 1000. So that, right, do the maths. If you have a calculator, do the maths, right? So that gives you 0.0157. Okay, fine. Now what is the range or what's the interval that shows 95% confidence, right? Already have done the maths. So it is, right, P cap plus or minus 1.96 standard error of P cap. So this is the standard error of P cap. Just now calculate, right? That means 0.55 plus or minus 0.031. Okay, I'll give you time, right, just to do the analysis. Let me finish this explanation. So 0.55 minus 0.031 is the lower one. Okay, and 0.55 plus 0.031 is the upper one. Now you see, it says that whatever P cap you calculated, from that I can conclude that actual value of P will lie between 0.51 to 0.58. So I had a question asked in one of the previous slides. This says that how can you make sure that the actual P when election results come, right, will not go beyond, will not become lesser than 0.5, which actually inverts the results which you guessed, right? So now you see I am able to, right, I'm able to do that. At least I can say that I got a p value which is something like 0.55, but now I can say that the actual p will be minimum 0.51, maximum 0.58. Okay, this is the range of p, that is the actual fraction, right, of the overall this. So minimum to maximum you are able to guess. So this is how the guess is made. So when I say, when you see the exit polls, people say that, right, a particular party might get say 250 to 320, right? 250 related to this minimum number 0.51. Okay, the highest number which comes because of the upper boundary we have. Okay, so the message means it is actually the mathematical term P equal to 0.55 with the 3% point margin of error, right? So how did you say that 3%? It is just because of this number. You can see 0.55 plus or minus 0.031. 0.031 convert into percentage, it becomes 3. Multiply by 100. Okay. So there is a 0.55 is, you can consider 0.55, but there will be a 3% margin of error. It can be reduced by this or it can be increased by this. Okay, yeah. Any doubt with this numerical example? Please feel free to ask. You want the previous slide? Yeah. Next slide. Okay. Okay. All right. Yeah. Ah, yeah. 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 I'll explain that. So this part is fine, right? So this is the P cap plus or minus 1.96. That number came from the table, right? Which is corresponding to 95%. And this is because of the standard error of P cap in the previous line. So multiply this gives you 0.031. Okay, that 0.031 into 100 is 3. Okay, that is the percentage. Okay, so 3% came just because of that. So last line says P equal to 0.55, that is this number. Okay, 0.55 plus or minus whatever you write, that is an error. So there is a 3% error of that. All right, good. Okay, do we have any other doubt? All right. So statistics says, right, you can actually bring in another variable that is also going to help you out, right? So that variable is called as the alpha. Okay. So just look at the equation for alpha, right? It is again related to our standard table itself. Okay. Alpha is actually 1 minus the confidence. Yes, Gaurav. Hmm. Yes. Yeah. Yes. You have to calculate the fraction p cap and use the p cap in that equation, this equation. Yeah. So you can see here, right? P cap into 1 minus p cap divided by n, everything under square root. Okay. That, yeah, for standard error of p cap, it's the same. Yeah. This is the form. Okay. All right. Any other doubt? Fine. So we are bringing another term over here that is called as alpha, right? It's a pretty straightforward. Instead of using a confidence level, they define it as a 1 minus confidence. It's something like confidence is 95%, right? Alpha says 1 minus that confidence. It means it is related to the error part. Okay. So if you have alpha as say 10%, the confidence level will be 90%. So that's what you see on the right side in the form of a table. Okay, so just look at the table. Here you can see the first row represents, right, confidence level. Again, this is a part of the table. The whole table is not required, just to understand the concept of the table. Okay. Now, confidence level means it is 1 minus alpha, because I just want to have a confidence level means take this to the other side, bring the alpha to this side. So this becomes 1 minus alpha. So wherever you write 1 minus alpha, that will be the confidence level. Is it okay? Fine. So confidence level, we'll take it as 80% confidence, 90% confidence, 95% confidence, 99% confidence. So far we were just dealing with the third column only. Okay, so just look at this. This is what we were dealing with. Yes, but you can define any confidence level, right? So I want to say that I want to get a confidence level of 90%. I want 99%, right? Okay. So any value you can choose. So few of the values we have shown. Okay. So if the confidence level is denoted by the first row, the second row, we convert the same thing into the alpha. What is that? 1 minus that. So 1 minus 0.8 is 0.2, 0.1, 0.05 and 0.01. Okay, very straightforward. Simply 1 minus the previous row, you get this one. Okay, now I am considering alpha by 2. That is because it's the error that is present on both sides. So consider this, right? Let's take the same example which we were dealing so far, 0.95. So 0.95 is the area under the curve within the confidence interval. So outside this, on both sides, I have equal area, right? So total error is 5%, 0.05. Right side, you will have half of that. Left side also, you'll have remaining half of that. So totally how much? Totally the error alpha denoted by 0.5. Okay, right? Total area of the error, which means, right, of not having confidence. It's an error, is a normal common term. You can call it as 1 minus, sorry, the alpha value itself. Okay, other than the confidence level, not having the confidence, right? So you can see that that is 0.05. Both sides I should have the equal value, so divide by 2. That's what we call as alpha by 2, right? It's again because of something plus something minus. That's why the alpha by 2 for plus or minus is written over here. Okay, so you can see this is 0.025, half of the 0.5. Now you see everything, everywhere it's the same thing on this side as well as on the other side. Whatever is the alpha value, alpha by 2 is considered. Okay, so corresponding to that alpha by 2, or right, at that point, whatever is the z value is 1.96. Anyway, you know that how we obtained 1.96, right? You went to the table, from the table, right? Whatever is the value corresponding to that, you found the z value, and that is the z which is 1.96. Correct? Just recall. Similarly, you can find other values as well, right? Corresponding to 90% confidence, if you want, you should use that number as 1.64. You don't have to write 1.96. For 95% confidence, this is 1.96. Okay, so for if at all you want 80%, you can multiply the standard error just by 1.28. At the same time, you want 99% confidence, means what is the number that you need to multiply the standard error? It is 2.58. So now you see, right, depending upon the confidence level that you want to obtain, right, for your range, right, you can use the specific level of alpha or 1 minus alpha. It's one and same. It's anyway, you can subtract from one to get the other part. Okay, so I hope this slide is also clear, right? Any doubt, you please feel free to ask. You can take any. Yes. No. You understood how to calculate, right? Only one part I have shown here. Any value you can take. Like 0.95, we actually did from very scratch, right? For 95 means divide by 2, right? Go to the table, find out that value, read the Z value. That's what is required. Same thing you can do for 70%, 50%, anything. Okay? Anything you can. No, it's obvious that you will definitely go, you will be away from 50, because 50 is where you have highest doubt, right? 50% means my mean is 50, means I can come on this side or I can go to other side, right? Which means your result can be yes or no, both, right? That's why always you try to move away from the 0.5. 0.5 is very dangerous, because 0.5 means your actual result may fall on the 0.45 side where you lose the election, or you may go to the right side where you win the election. So that's that dilemma, right? You cannot say that which is the correct answer. So always you move away. That's why these points which I have shown here, right, they are very far away from 0.5. Correct? I want to make sure that I will tell you a result that you will win with so much confidence. That's my idea. So I took an example of 0.95 only because of that. So 0.95 you choose means you will at least get 85 or more than that. Correct? Because 95 minus something you may reach 80, 85. Fine. Other than that, on the right side, definitely it is 1, right? So that is the reason. Yeah. Yes, you see. Closest one. Yes. Closest value you can choose. Okay. Whichever, you may have two values over there. Whichever is closest to the one which you are looking for, you take. All right. this. Any other doubt? Okay, so we are proceeding further. Now we'll go to another very important part. Okay, so how can you further increase the how can you improve this further? In a sense, I have a confidence, right? I want to increase this. So, right? So I have so much of width available, right? If you increase this further, you are in the sense the 1 minus alpha, right? You are trying to increase means alpha is decreasing, right? Error not having confidence will decrease. So this region you need to increase is the first point. Increase the interval width. Okay. Improve the standard error, right? So both are fine for us, right? I can do both of them, right? But now you see, go back to the original problem of hitting the target, right? It says, right, larger the circle. Previously we considered the circle is of radius 10. Okay, now try to increase, make it 20, right? Now the chance of getting the bull's eye inside the circle becomes more, right? Because it's a bigger circle, right? So that's the second point. Larger the circle you draw around the point, we have higher probability of this. So that means if you increase and consider the whole, right, board, it's 100% definitely, because it will be there inside that particular board for sure, right? Right. So if at all you try to reduce the circle's radius, right? So that means standard error is smaller the radius, right? Radius will be smaller. But if I say that, yes, I reduce this and still the point, the bullseye exists inside that, that means you are more confident, isn't it? So when I increase the radius, you are not increasing the confidence level, right? You are reducing the confidence. But if I reduce the size of the radius of the circle, then what you are trying to do, you are trying to increase the confidence. I'm saying that I reduce it to 5 centimeters, still I say that yes, the bullseye will be inside this circle, means it is larger confidence, smaller the radius. Okay, so I'm trying to relate things now. So actually what happens, we'll see. Right, so I'll try to increase the sample size, right? In the sense, I'll ask more and more people about, right? So okay, let's say we have the sorry, yeah, so we have the distribution available with us. Okay, so that's the distribution. So we will call, we'll put a term here. The term is called as the half of the interval width. Whatever interval you have, it's a half of the width. So 0 to some number you have, right? So that is the error term, let's call it. So how do you calculate the error, right? Error is nothing but the z of alpha by 2. It's actually nothing new. Already we have done that. You see here. So this part I'm talking about, this is what I'm calling it as z alpha by 2 into the SE, right? Into the standard error. So standard error is calculated as p cap into 1 minus p cap divided by n. So same thing, nothing changed, only notation changes, that's all. Okay, so don't get confused, it's not a new thing, it's z of alpha by 2, okay, p cap into 1 minus p cap divided by n, right? That is equal to error. I'll call that as error. So what is this error? Previously you remember the error was called as 3%, right? I didn't expect that error, but because of the calculation, the error came to be 3%. Okay, so now I'll modify my point now. So just concentrate. So what I'm trying to do here is that let me choose the possible error. Previously it was 3%. That after calculation I came to know that that is 3%. Now I will make sure that the maximum error I expect is just 1%. That means E, I will put it as 0.01. Okay, so that means I'm expecting only 1% of error. More than that is not accepted. Okay, so I'm only deciding. let's say that so somebody may say that, no, I expect 5%. I am okay with that, right? So they can put 0.05. So we are the ones to choose what is the accepted error. So that is capital E. Anyway, this Z alpha by 2, right, has to be chosen according to your confidence level, right? If I say 1% error, what is the Z value? It should be corresponding to 99%, correct? If at all you are saying that I'm okay with 5%, E will be 0.05 and Z alpha by 2 will be 1.96. Okay, so how to judge this, how to calculate these values, we already know now. Only thing is some modification required now. I'm coming to it. Okay, I already have sampled, right? I have done the experiment. Out of 500 people or 1000 people, how many are in the favor of candidate A, right? I know that. So using that, that's a fraction, I calculate this. Okay. What if, right, the n which I'm going to put here will not give me this error, which I said. I said I want 1%. But if you do 1000, if you ask 1000 people, it is going to give you 3%. It's not 1%. Now the point is that you need to increase n such a way that you get the expected error. Only that's the solution, because Z alpha by 2 is fixed. I want 95%. Z alpha by 2 is fixed to 1.96. I cannot change. P cap 1 minus P cap, no, we cannot change. Okay. Capital E is the one which I expect. I expect 1%, I expect 5% fixed. So only one parameter you can change is the number of people you sample, right? 1000 gives you 3%, no problem. If I want 1% error, I have to increase n. What is that n? Just see here, right? So the above equation has been modified to get this. Okay, square both sides, move n to the other side, take the e to the other side, you get this answer. Okay, anybody having doubt, please raise a question, right? How to get this? Do you have any doubt? From E equation, that's the first equation, I'm getting the second equation. Do the maths. Huh. So standard error is only one term. Okay, I'll just go back. I'll show you that. So see here, this 0.0157 is there, right? This is the standard error, SE. This total thing is the error, E. Okay, all right. Okay, anything else? Any other question related to this? Okay, now you see, we have another situation here. When I just don't get confused with the notation. I think I didn't notice that. So you see here, there is a P star and 1 minus P star. Don't get confused, it's the same as P cap. Okay, it's a typing mistake, that's all. Sorry about that. So please make sure that P cap 1 minus P cap, same thing here. Okay, the cap is by mistake printed as a star. All right, it's a P cap into 1 minus P cap. All right, so what's the problem with this? Go to the next point. It says that P cap or P star is not known. Are you okay with that, or do you have doubt? Previously we were saying that P cap is known, P cap is known. Now I'm saying that P cap is not known. So how is it possible? Anybody who can answer that question? Think about that and try to answer, right? So far we were saying that, yes, I know P cap, I know P cap. I want to relate P cap with P. Yes, now I have an equation and now I am saying that P cap is unknown. How is it? Now the n is different, right? Perfect. Yes, you see the P cap which I used to say that I know P cap, right? That was a different n, like 1000. 1000 I know the P cap. But you see now I'm changing the n to a different value. I am calculating n such a way that I get the required error, right? Error I changed. 3% was the error. I changed it to 1%. Now that means what? For 1% error, you need to change your n. What is that n? The equation number 2 says that, okay, this is the n you need to calculate. But when n changes, the p cap will should definitely change, right? P cap is a fraction. When I asked 1000 people, they said 550 people said that, yes, we voted for you. But when you increase 1000 to 10,000, it's not necessary that 5500 will say that, yes, we voted for you. It may be different. 6800 people may say that, right? So you see P cap changes. Okay, so that is the issue here. We have a very simple solution. We will put the worst case, right? I just mentioned that what is the worst case of the probability, right? Just now somebody asked a question, can I put any value, anything like 0.5? I answer that, move away from as much away from 0.5 as possible, because 0.5 is dangerous. That means 0.5 is the worst case, right? You move away from 0.5 in any direction is fine. Okay, I move 0.5 away from 0.5, I make it bigger, right? 0.8, 0.9, right? 95. It is good in positive direction. In the sense, yes, my answer is yes, he is going to win. No problem. You move on the other side. From 0.5, I move away. 0.3, 0.1, 0.05. Your objective is yes, you will lose the election. That's all. But when you come to 0.5, it's a dilemma, right? I may move this side, I may move other side. P may be anywhere. So that's the worst case. So put P star or P cap as 0.5. See the next point. So the whatever after the election we get the prediction, right? Everywhere they are going to put the 0.5 in the worst case they are calculating. That's why you see the larger gap between the minimum maximum number of seats that this party is going to win. They will never come closer to, they will not come closer to this, because they have opted for a worst case. Okay, so they will always choose something like 0.5 over there, and the calculation will be done, and you will see that, okay, 280 to 350. So it's a huge margin. Nobody will say that you will get only 310 to 320. No, nobody will say that. Okay, because of the same reason, right? So if you reduce that, means, right, more error possible. So see that point, right? We choose P cap as this number. All right, so that's the reason. So now let us do a quick calculation, right? Below that you can see some calculation is being made up, right? So let us take that, the E, that is the capital E here, right, which is substituted here, take that as 1%. 1% means what? 0.01. Okay, so E square, you can see that I'm substituting this to this equation. E square is substituted as 0.01 square, right? So what is the Z alpha by 2? For 1% error means what? 99% confidence. Corresponding to 99% confidence, I have a Z value 2.58. So you see, P cap is 0.5. Okay, I'll answer that again, right? So you see, if you move close to higher than 0.5, it means you are going to make a bias, saying that, okay, this person is going to win, but I don't know. Okay, if you reduce that, if you reduce 0.5 lesser than that, you are indicating that you are biased towards this person losing. Correct? I don't know that, right? So make it equiprobable. 0.5 he will win, which means 0.5 he will lose. Okay? Yes. Yes. All right. So substitute. So to this equation, right, we are substituting the values. Okay. So Z alpha by 2 square is 2.58 square. P into 1 minus P will be same, 0.5 into 0.5. So 0.5 square is being written over here, right? Divide that by 0.01 square. Now you see this says that 16,641, right? What is the meaning? How do you decode this? It says the number of samples n is equal to 16,641. So what is the meaning? In order to get a 99% confident prediction, if you want to make that prediction, 1000 is not enough. We started with, say, something like 500, right? 500 people we we try to talk and we get a result, P cap was calculated, etc. Then we move to 1000. Now you see the meaning is that 1000 is not at all sufficient, not even close, right? You want a 99% close result, means how many people you should talk? You should talk to 16,641. So you see, you are coming closer and closer to the P. The number of people you need to talk is increased, right? This is 16,641. Okay. At the same time, for 95%, it's a different number. You don't have to go with that. Okay. Can anybody quickly calculate what is the 95% confidence? How many people you need to talk? Can you calculate? 1.96 whole square into 0.5 square divided by 0.05 square. Okay. Let me also do the maths, right? So you also do quickly. Let's verify our answer. Okay. So Z alpha by 2 is 1.96. All right. So it's a square of that. Then 0.5 will remain same. So you please write 0.5 square. Okay. Then divide it by 0.05 square, because there is a 5% error. When I say 95%, 5% error. Yeah. Anybody? Yeah, that will change. 90, yeah. So for that, right, you need to refer to the table which I had shown earlier, right? So this is a table. So 95% means I am supposed to use Z is equal to 1.96. Okay. Yeah. So according to your preference, you will choose a confidence level, right? According to that level, you need to use a Z value. Okay, now my question is 95%, so 0.95. So Z value, Z alpha by 2, you are supposed to use is this. Okay, use 1.96. Yeah, we have one answer, 9604. Okay, others? It's a 1.96 square into 0.5 square divided by 0.05 square. Right? So let's do that math. Okay. Okay. Yeah, anything normally more than 95. Okay. Yeah, more than 95 is preferred. Okay, you want to move as much away from 0.5 as possible. That's all. Right? Yes. Yeah, others, please put your answers in the chat box. Okay, we have two answers only. 19604, 385. Yeah, Ruchi saying 385. All right, let's verify. Others? You have the equation readily available with you. I also mentioned what are the values to be substituted. Simply put those values, you will get the answer, right? So please do that, everybody. I need a few more answers. Okay. Okay, it's N. So Somesh, I don't think you will get 0 point over there. A whole number, it's a number of people, right? So 0.38 may not be the right one. Okay, so please check that once again. Yeah, others? So we get a value, when I calculated, I'm getting 384.16. So it's a whole number, so we'll make it to the next number. Okay, so 385, right? That is correct. All right, fine. So now the idea is that at least I know that I may not be able to say guess the p value. Actual p value we are not able to, but at least to say that, okay, with so much confidence, if you want to give your answer and predict that, okay, this will be the p, right, range of p, right, you should know at least, okay, these many number of people I should talk, right? I should consider so many samples, right, before I give a solution. So now you see that, okay, out of these many, right, this is the population of the country, right? If you want to get a 99% confidence on your exit poll, how many people you are supposed to talk, right? So that's the calculation which those TV people will do that. Okay, so ultimately, once again, we are still having some issues with the sampling only, which we never consider. Initially, I told that, assume that, right? Just remember, I exactly mentioned the same words over there. Assume that, right? Whoever told that I voted for, right, person A, right? There is a catch, right? I told that, okay, they told that, let's assume that they told the truth, right? Again, there is a catch. So, right, ultimately, I'm talking about the sampling, right? The way you do the sampling matters, right? And right, there are some other conditions. We are going to talk about that. So sample size is fine. I came to know that 99% accuracy, if you want, you have to go with 16,000 and odd number of samples. Okay, right. Now, if you, this assumes that purely random sampling you have performed, right? And we know that simple random sampling is not possible under the standard condition. Okay, practically we cannot do that because there are conditions like you should be unbiased, etc. Many things are there. But you see, in a practical scenario, when you do that, there is a bias. There will be bias. You cannot avoid, right? First thing is that, right? Then the bias can also exist in the following three fashions. These are also considered as the versions of a bias only. Response bias, in the sense, the whoever you talk, he or she lied. They said that I voted to this person, but actually they voted to another person. Right? So that will bring some error in your calculation. Okay. Now you see, most of us are active only on the right platform, other platform. We don't go for voting, right? We say that we are very active. Okay, well, this is the party should win. This is what should happen. Everything we'll say, but we'll never vote, right? So that's the second category. Poll responder did not go to vote. He simply said that I voted to this person. You calculate with him. Okay, there is a vote percentage like this, but actually, what happened? He never went to vote. Okay, and right, the third is also a bias, but that is better than the other. You see, voters did not participate in the opinion poll, right? So in the opinion poll you don't get his view, but anyway, his actual voting will be considered for this. That's also going to generate an error, but right, it's okay. Right, so what the actually what people do, I'll tell here. Okay, again, that has nothing to do with our calculation. We have done the calculation and we understood the maths behind that. That's what was very important for me, right? So now what we are going to discuss is what exactly people do, right? So they use, right, what you call as various models, okay, to reduce the sample size cost. What is the cost? Right, I said that these many people voted, like 16,641 I inquired, out of which everybody told that I voted, yes, I voted to this person. But because of the bias that is existing, you have small variation. So actual value and this 16,641 which I interviewed, right, I talked to them about the opinion, right? So there is a gap, right? There is a difference, right? That is what is the cost, right? So that is what is the size cost of the sample. This should be minimum, right? Out of 16,641. So in order to come closer to the actual number of votings that might have happened, you may have to do some method. So that's what is called as the different models. All right. So maybe a simplest model is you take 10% more people's opinion. You don't stick to 16,641 because there is a trend that 10% of the people have some bias. Okay, again, that's just a model. I'm not saying that you have to do that or people will do that. That's just an example, just to make you understand. I said that different model I need to justify. One model is that don't stick to 16,640, whatever number you get, take 10% more of that. In the sense, add 1,700 to that, approximately 1,700 more, 10%. So then this will be right nullified. Okay, so out of 16,000 plus 2,000, let's say 18,000 if I take, so there is some error, it will come down to 16,000 something. So I may get an approximate percent. This is one type of model. Okay, and some other techniques are available, which is an estimate, right? So that is actually, they try to represent three parts in their estimate. One is because of the truth, and one part is because of the bias, one part is because of sampling error. Again, this is just another model, that's all. Okay, let's not go in depth about this. So since we were talking about this whole poll process and the exit poll so far, right, it becomes necessary to understand what exactly happens on the plan. Okay, so the maths will not do that. So then they will fit a model, right? It's actually called as a regression, right? So estimate the bias and sampling error through what is called as a regression, right? Regression is prediction. All right. So out of this estimate, they need the sampling error, the bias, etc. Right? They are a part of your model. So you can guess that, right? You can estimate that by using regression. So like classification, you have another set of problems that can be solved by using machine learning, deep learning, etc. And they are called as a regression problems, right? Regression, I think I might have given an example, I don't remember, but let me tell you. So the stock market closed, right? So on Friday, right? What will be the stock market opening price on Monday? I can make an estimate. That is the regression. I use the last 10 days of stock market price, right? Maybe a specific stock, right? I use them and I predict what's going to happen, right? So that is a regression problem. So like that, right? Use the bias and the sampling errors of the previous data, whatever you have, and make a prediction of the current bias and the sampling error, so that overall you can get a estimate, right? Closest estimate that is possible. Okay, so far any doubt? All right, so we will move further to a poll. Okay, so okay, let me check whether I can bring another poll. Sorry, it says that poll is inactive. Okay, I don't know. All right, please type. I don't want to waste time over there. Okay, creating a poll. Please put your answers in the chat itself. Okay, so just look at that and try to answer. Okay, don't type everything. So just write 1.1. If your answer is first one for the first question, 1.1, 1.1. If your answer is third one for the first question, put 1.3. I love it. Okay. So for the second question, 2 point something, 2.1, 2.3, 2.4, like that. Okay. Third question, 3.1, 3.3, 3.5, whatever. Ah, okay. Even if you write, that's also fine for me, the whole answer. But the first one, you may have to type the whole word, right? So I suggested go for 1 point something like that. Yeah. Okay, everyone, please put your answers in the chat box. Try to recall. I'm making you to recall the everything we discussed after the previous poll. Okay, so that's why Take some time, no problem, right? Try to put your answer. It gives some idea about whatever we're going to use next, right, is related on all these. That's why I'm trying to make you people to think about that. Okay, right? Okay, others? Okay, 30 seconds more. Anybody who didn't answer, please try to answer. Okay, so let's look at the answers one by one. So the first question says that the sampling distribution of the fraction estimator is, right, what's the way it is distributed, right? So we are looking at the fraction, right? Fraction denotes the p cap. So, right, we understood that we converted that p cap into z, right? So means what is the distribution? It's not Bernoulli, it's not Poisson, it's not binomial, it has to be normal, because p cap was converted into the z, right? And right, we did the other part of the calculation. So let's remember, right, for the first question, right, we have answer that is 3. 1.3 is the expected answer. Okay, then what's the z value for 95% confidence? Yeah, yeah, please. Fraction in the sense the p cap, right? P cap is a fraction, right? Out of 1,000 voters, how many voted for me? Right? So that's a fraction. We are estimating the fractions only, right? So that's why it is called as a fraction estimate. So new term has been used. That's all. So far I never used that word. I use that word now. So it's expected that you understand. Fraction was the one which we were calculating so far. I am estimating the p. Correct? P is nothing but the fraction, actual fraction of the total constituency, the whole constituency. Okay. All right. When you are having a large number of say samples, right? Everything tends to be normal. So irrespective of others, you will always move to the normal. Okay, sure. Okay, then the second part, Z value of the 95% confidence interval. We have used this several times, so this has to be 1.96. Okay, so we have even done the calculation using the table, etc. Right? How to obtain that? We have done that. So any other value asked, you know how to calculate. Okay, so that is what is the second question. Answer to the second question, 1.96. And the next part is half width interval width. right? The half, right? Only on the right side, what is the area? How do you represent that? It is not alpha. Alpha is what? Alpha is 1 minus confidence. That is the error part. So it's not that. So omega we never use, so that's ruled out. Capital R, I don't think we have used. So E is the one, right? Because E is nothing but Z alpha by 2 into the standard error, right? So that is the one which is going to give you, right, the part, that is the E, right? So that's the E part which corresponds to that. Okay. All right. So let's move further. Now, so far we were discussing everything related to the fraction, which was the first property we discussed, right? So initially I told that, okay, initially we are going to discuss about the first property, that is the fraction. Okay. After the fraction, let's move to the next property we discussed, right? We defined that there is a second property, which is the mean, right? So we also discussed some of the examples which said that, okay, average height of students of age 4 to 8. See, that's average. Right? We are not looking at the fraction in this example. So, right, let's see the question here. We want to find the average height of children between certain ages, say 6 to 12. Right. I want to find out the average this thing. So how do you normally calculate an average? Average means I have to measure every height. So I have to ask every child about the height, right? Who is between 6 to 12, right? Calculate and take a sum of their heights. Divide that by the number of samples you took, right? But anyway, it's obvious that we cannot measure each and every child. Okay, so always what you can do, you can take samples, right? All over India, if you want to calculate, okay, every state, right, some samples you might have to take. Right, now again the idea still remains same. Previously we were looking at the fraction. What fraction of votes some person is, a particular candidate is going to get, right? So that was an estimate we are supposed to do. Now it's not the fraction that we are trying to find out, we are trying to find out the average, right? Now what guarantees that the mean that you say, okay, I measure the heights of say 100 children, okay, and I'll say that the height which is obtained is say 4 feet, right? What are the guarantees that the sample mean is same as the actual, right, average of the whole population? All right, so the last sentence is what I just mentioned, right? So we were asking the question that sample fraction for a particular given sample, we try to calculate what is called as the fraction, right? For a small population, you can. Okay, how you can be so sure that, right, the fraction you obtain here applies to the whole population, right? We did a match, we did everything. Now we are fine with that. Okay, so in order to make a confidence with the confidence level you want to answer that question means you need to take so many samples. At least that we know now. Okay, similarly now we have to bring the maths for the second part of that is the mean. How the mean is going to, right, distribute it. So you see now the heading is sampling distribution of mean. How this mean, right, is distributed, we are trying to do that calculation now. Okay, so again sampling is absolutely necessary. I start with the sampling only, right? I want to answer this particular question. What I try to do, I'll always start from, right, sampling, right? So maybe you start with a smaller number of samples, right? You don't calculate the fraction now, you calculate the average value of certain thing, right? In this case, that is the height, right? So whoever you meet, you ask what is your age. If the age is between 6 to 12, you will measure the height. Like this, you take sample, right? There is a population out of which you take certain sample and do this, right? You get an average value for the the height. So our next question that we are supposed to answer is only one thing, right? How can you be so sure that this particular average which you have calculated by considering only 100 children is applicable or is close enough to the actual average of the complete population? Okay, I hope things are getting more and more clear now. Okay, I don't want to move to the next topic because it will be left in the middle if I do that. Okay, so that's what is going to come in the upcoming class. That's going to happen tomorrow. All right, so meanwhile, if you have any doubt, please feel free to ask.